Okay. Yeah. So everyone is. I think everyone is here. So, because actually for 2 weeks, we will provide only online classes during the 2 weeks because uh, actually this is the midterm exam period, so we don't have enough classroom due to the COVID-19 pandemic situation. So we will provide the only online classes. So we are learning about the out-of-order process architecture. So actually, this is the backbone of the modern process architecture, which means that modern processors, most of the modern processors employ this out-of-order process architecture. And then, so you need to remember that why do we need to? So in order to increase the performance, we need to use the out-of-order process architecture. But why? Why? Why do you use these out-of-order process architectures in the modern process architecture? Why? You can find an answer on this slide. The answer is, so we need to increase instruction level parallelism. So it means that, so what is instruction level parallelism? Hey guys, can you turn on the camera? Okay. So why do we need to exploit instruction level parallelism? And then what is the baseline? So why actually, so let's start from the pipelining architecture, which means the static pipeline architecture. So why do we use pipeline architecture in our process architecture? Yeah, so in order to increase the performance, so how can we improve the performance in the pipeline architecture? So this is very important, actually. Oops, not happened. Okay. So we need to exploit instruction level parallelism. Okay. So which means, so what is instruction level parallelism? So if we can exploit the instruction level parallelism, then we can increase the number of instructions which are being executed in the processor. So exploiting instruction level parallelism means, so increasing number of instructions which is being executed. So it's running. So which is learning, which are learning inside of a processor. So if we increase the number of instructions which are running inside of the processor, then we can increase the performance of our processor. So I believe you can remember so we can increase the performance of our processor by using parallelism. Okay, so actually in the first or the second class, I explained we can increase the performance of a processor by using parallelism. Because actually, there are many kinds of parallelism. So we can exploit the instruction level parallelism. So actually, the pipeline architecture or out of the process architecture exploit this instruction level parallelism to improve the performance. Also, we can apply some other level of the parallelism, such as the thread level parallelism. So which means that we can increase the number of threads which are running inside of a processor. So for example, if we use the multi-core processor architecture, such as Intel core architecture or some Intel sub-architectures, then we can increase the thread level parallelism. So which means we can also increase the performance of our computer system. So which means we can increase the performance of our processor by using parallelism. Okay, so actually we are learning about some architectural techniques which can exploit the instruction level parallelism. Okay, so this is very important for the performance of a processor. Okay, so I explained about the data hazard. So this is also very important. So we need to avoid the data hazard on registers and memory. Okay, this is very critical problem. So we need to consider the 3 types of data hazard, like low hazard, warhead, and wow hazard. So okay, and then I also explain how can we develop the Thomas law algorithm. So this Thomas law algorithm is the baseline algorithm that implements the out-of-order processor architecture. So okay, so actually this architecture has been developed from the static pipeline architecture. Okay. So this is the Thomas law algorithm, and then Thomas law algorithm is composed of front-end part and then back-end part. So front-end part prepares the instructions to be executed by execution engine, and then back-end part actually execute the instructions which are ready for execution. Okay, so we can classify the Thomas law algorithm to the front-end part and then back-end part. Okay, and I also explained about the front-end part and then back-end part of the Thomas law algorithm. Okay, so I also explained about some memory, the data hazard on the memory. Okay. Okay. And then let's think about the control hazard on the Thomas law algorithm. So I already explained about the disadvantage of Thomas law algorithm. So the first, so actually, in order to increase the performance of a processor, so which means that I already explained that we need to increase the, actually, I turn off my video. I did not realize. So actually, we need to increase the number of number of instructions which can be executed in the processor. But the disadvantage of the Thomas law algorithm is that when the instruction is executed and then the result of the instruction is updated immediately on the register file. Okay, so if you see this architecture, then you can find that when the instruction complete the execution in the execution engines, then the result is delivered to the CDB, common data bus, and then as you can see, the result is delivered to the registers. Also, this result is forwarded to the issue queues. Okay, issue queues. So problem is that when the instruction is completed, its result is stored to the register file. So what does that mean? whenever instruction is completed, its result is stored. So which means that the result of instruction is committed immediately. That is the disadvantage of the commercial algorithm. And then the instructions are updated on the register file or memory. So you need to remember that this is very important. If the result of instructions are updated on register file or memory, it's very critical. It's very hard to cancel the result of these instructions. Okay, so we cannot roll back the state of the computer processor in this case. And then problem is that there are many conditional instructions in our codes or in our applications, like conditional branch instructions. So which means that when the branch instruction is executed based on the result of the branch instructions, the execution path in our application can be changed. So which means that we don't know. We don't know the exact result of these branch instructions, but which means that this branch can be true or false. So, but in order to execute the instructions after this branch instruction, then we need to select one of the paths from this true path and false path. So if you select the maybe true path, then we can execute some instructions after this conditional branch. But what's the problem? When the execution of these instruction is completed, then the register is updated. So register data are updated by these instructions, but we cannot cancel the result of these instructions if the branch is resolved as false. Okay, so the problem is that the Thomas algorithm, if the computer processor encounters the conditional branch instructions, then this computer processor needs to stop dispatch of the instructions after this conditional branch instruction. Okay. The problem is that, what is the problem? Instructions, completed instructions are committed immediately. That is the disadvantage of Thomas law algorithm. Oh, the problem is that, so I believe I mentioned repeatedly during the classes. So actually, these conditional branch instructions are observed in our normal applications every 4 or 5 instructions. So which means that the percentage of a branch instruction is about so less than 20, but it will be higher than the 15%. So which means that every 4 to 5 instructions we can find conditional branch instructions. So what does that mean? On average, we can find only 5 instructions. So which means that the size of the basic block in our normal application is about the 4 or 5 instructions. So a single basic block may include the 4 or 5 instructions. And then actually Thomas algorithm is the out-of-order processing architecture, but this out-of-order processing can be applied inside of a basic block only. So which means that if the size of a basic block is very, very small, the advantage, we cannot enjoy the advantage of what is Thomas algorithm or out-of-order processing. So we can just find the small number of instructions in a single basic block. So, but I explained that in order to increase the performance of a processor, then we need to find many instructions, as many as instructions which can be executed in the processor. Okay, so which means that we need to exploit the instruction level parallelism, but because of the conditional branch, so we cannot exploit the instruction level parallelism in our out of order processor architecture, and that this is the very severe performance bottleneck in the processor. So we need to solve this problem. But you need to understand that in the original Thomas law algorithm, we cannot if a processor encounters conditional branch instructions, then we cannot execute instructions after this conditional branch instruction. Okay. So, and then another issue of the Thomas law algorithm is the Thomas law algorithm cannot support precise exception. Okay. So why? Why? It's obvious because then how can you support the precise exception? In the static pipeline architecture, not to support the precise exception, then we need to force the order of completion, right? Do you remember? So in the static pipeline architecture, in order to support the precise exception, I explained that a processor need to force in order completion. Okay, but this is the out of order processing. So and then in the Thomas algorithm, out of order processing means out of order completion, which means Thomas algorithm cannot support a precise exception. It's not supported. That's another problem of another disadvantage of Thomas algorithm. Okay, so here. And then I believe I already explained about the memory disambiguation of this Thomas algorithm. Also, so actually, so then how can Thomas law algorithm support out of order processing? And then how can Thomas law algorithm solve data dependencies like data hazard for low hazard and the wow hazard and war hazard? Actually, we call the low hazard is the true data dependency. What does that mean? So actually, low hazard is caused by producer and consumer of the between two instructions. So which means that we can find the low hazard, like the low hazard data dependencies between two instructions. If the former instruction is a producer, and then the following instruction is a consumer. Okay. So because of the producer and then consumer dependency, the low hazard is observed in our applications. And then these low hazard dependencies are frequently found in our application. And then this is called the true data dependencies, right? But how about the war hazard and then wow hazard? If a computer processor supports the atomic execution, so which means that when an instruction is executed, the result is updated immediately. So that is the atomic instruction. So, but if the computer can execute the instruction automatically, atomically, it's very hard. So if we computer processor support the atomic instruction execution, then we don't need to consider about the war hazard or wow hazard. So why do we need to consider war hazard and wow hazard? So we already learned in the static pipeline architecture. We need to consider war hazard or wow hazard because of out of order completion or out of order processing. And then, so which means that the latency of instruction varies. Okay. So because of these latencies of instructions, then we need to consider the war hazard and wow hazard. And then how can Thomas Law algorithm solve war hazard and wow hazard? So if you see the war hazard or wow hazard, it is related to the write operation. Okay, so which means that add x1, no, this is not a risk 5. Add r1, r2, r3, add r1, r4, r5. So if you see that these instructions, you can find that, oh, R1 is the same, but we know these actually the data for R1 and for this number 1 add instruction is different from the data of R1 of number 2 add instruction. So actually the R1 is different. Okay, so actually these two add instructions have the destination register, the same destination register R1, but actually data stored in this R1 by add instruction 1 and then by add instruction 2 are different. Okay, the data are different each other. So how can you solve this wow hazard? If the data is different, and then if the destination is different, like, oh, this is the R1, this is the like R100, for example, this is the R destination register is R100. And then for the second add instruction, destination register is R101. Then we don't need to consider about the wow hazard in this case. So how can we solve the wow hazard or war hazard? If we use the different registers, different destination registers, then we can solve this kind of data hazard. So this technique is called the register renaming. So we will learn about the register renaming later. But Thomas Law algorithm actually employs register renaming technique implicitly. What does that mean? When the instruction is issued, so actually the instruction is dispatched, then Thomas Law algorithm change the destination register number to the issue queue entry number. Right. So actually, it's very small. So add R1, so add R1. And then if the first add is dispatched to this issue queue, then this R1 is changed the issue queue number, like the tag of this issue queue. So it is changed to the like tag 100. Okay, and then so this tag is logged in the register file also, so which means that, oh, this register file will be updated, but it's not yet updated. The instruction is dispatched, but this instruction is not completed. So this tag is here. And then the following instruction can use the same tag for the low hazard case, like the following instruction, for example, sub R5, R1, R9. So because the R1 is changed to the tag number, like tag 100, the sub instruction need to consume the result of this add instruction R1, but this R1 is changed to the tag number. So when the sub instruction is dispatched to the issue queue, then this sub instruction use the tag number, tag 100 instead of R1. How about the following add instruction, R1? So in this case, actually the destination is the same, but we know this add instruction is the latest instruction, okay? So R1 is changed to the different tag number, like tag 101. So when the add instruction is dispatched to the issue queue, then another tag is used, and then this tag is changed to tag 101. Okay. So actually, we can solve the wow hazard or war hazard using register renaming. Okay. In the Thomas algorithm, register renaming is implicitly applied using tag number. Okay, tags. So you need to understand this in order to understand some out of order execution. Okay, so basically out of order execution is developed for solving wow hazard or war hazard. Okay, not so actually the row hazard is the true dependency. So it can be explicitly, we can analyze the data dependencies for low hazard very easily, and then we also this low hazard can be maintained explicitly. So it means that we can easily analyze the data dependencies in the different instruction for the low hazard. But for the wow hazard and wow hazard, then we need to change the destination register number for right. And then Thomas algorithm applied this register renaming using the tag numbers. Okay. So, and then, so you need to understand that this, because the same technique is applied to the like a speculative execution, and then real buffer, and then some other out of order process architectures. Okay. The baseline theory. So baseline theory is the same for the different out of order process architecture, but some like tags or physical registers or some real buffer entry numbers. So actually we can use the different data or different index numbers or different physical different things for implementing for implementing out of the processor. Okay, but the baseline theory is that we can employ register renaming, and then by employing this register renaming technique, then we can apply the out of the processor architecture. Okay. Okay, let's see the example. So this is the example code, which example code which is running on the Thomas algorithm out of the processor. So if you see that this code, you can find, oh, this is the floating point load instructions, and then this is the floating point add instruction, the store instruction, and then these instructions are used for calculate the offset of this base address for array. Okay, and then this is the conditional branch instruction. So if you see that these instructions in this code, so we can find, oh, these are load instruction, and the load instructions are executed in load store unit. Okay, like so this is the load instruction is issued to the memory unit. And how about this floating point add instruction? So this instruction is issued to the floating point unit. And how about the store instruction? So I already explained that store instruction is split into two different instructions. Okay, the first instruction is to calculate, is used for calculating address of a store instruction like SSA. So address is just calculated, and then the second instruction is the data execute the data transfers between register file and memory instructions. So store instruction is split into two different instructions. And then these are integer instructions. And this is the conditional branch instruction. Also, conditional branch instruction is executed by integer unit. Okay. Then let's see how these instructions are executed in the Thomas law algorithm. So in this table, you can find the number here, and then each number represents the clock cycle number. Okay, and then the each stage like dispatch and the issue takes one clock cycle, and then the execution cycle is different by execution units, and then normally the integer unit consume only one clock, but floating point unit, let us assume that the floating point unit consumes 5 clocks. Okay, so we just use the 1 clock for calculating addresses for memory instructions. And then how about the cache? So we assume that every cache access is hit. So we assume the cache access takes 1 clock. And then CDB. So this is very similar to the write back of the static pipeline architecture. And then when the data is delivered on the CDB, then we assume that it will take 1 clock. So how about the first load instruction? So let us assume that when the instruction is dispatched, then that is the first clock cycle for executing these instructions. So when this load instruction is dispatched, then load instruction consumes 1 clock, and then load instruction is issued to the issue queue for load store unit. Okay, so you can find this memory instruction unit. So I frequently use the load store unit for this memory instruction. So if the issue queue is not full, so this is also queue, so queue size is limited. But if this queue is not full, then the instruction can be issued. Okay. No. So sorry about that. So dispatch means that the instruction is delivered to the issue queue. So which means that the instruction can be dispatched if the issue queue has available slot. Okay, sorry about that. So then in the dispatch, the instruction is dispatched to the issue queue. Okay, and then when the execution unit is ready for executing instructions, then the instruction can be issued. Okay, so this is the first instruction. So let us assume that this R1 is ready. Okay, so so the data of R1 exists in the register file. And then the address is generated, and then cache is accessed, then it's delivered to the common data bus at clock cycle number 5. Okay, it's a write back, same to the write back. How about the second load instruction, I2? It's dispatched to the next cycle, issued, and then address is generated and the cache is accessed. And then at clock cycle 6, the data is delivered on common data bus. How about the add instruction? So we can find the true data dependency between this add instruction and the former load instructions, right? So we can find the data dependency. The low hazard data dependency, like here and here. We can find that some other data dependency here, but this is the latest instruction. So we need to consider the data dependency between I2 and I3. So what's the problem? In order to execute this add instruction, the data should be ready. And then when the data is ready, when this data F1 is ready, here. So data is read from the data cache, and then if the data is ready, and then this data is delivered on common data bus. Okay, and then if the data is delivered via common data bus, and then this data is also delivered to the issue queue of the floating point unit. Okay, so after data is delivered via common data bus, then this instruction can be issued at clock cycle 7. Okay, and then it's executed, it will take 5 clocks, so it's completed at clock cycle 12, and then it is written back via common data bus at clock cycle 13. How about the store instruction? Do we have any data dependencies here? Here. So, but if you see this store instruction, so store instruction is split into 2 different instructions, right? So this store instruction is used for only for calculating address. So actually this store A just use the R1. Okay. How about this store instruction? This store instruction need to wait until the F2 is completed by I3. So add instruction, right? So for this first store instruction, for store instruction for address, then this store instruction can be executed immediately because we just use the R1. So address can be generated. But the second store instruction, so data store instruction, then this data store instruction need to wait until the F2 is ready, right? So when this F2 is ready, here, right? So when the add instruction is completed and then the result of add instruction is delivered on the common data bus, then this two instruction can be executed and access the cache here. So can you see why we split the store instructions to the address part and then data part? So if the address is, if we just use the united store instruction, it's actually the original store instruction, then store instruction has the 2 source registers, like so data part and then the address part source registers. So which means that we need to check the 2 source registers for the low hazard. So which means that store instructions cannot be issued because of the data dependencies. But if we split the address part and then data part of the store instructions, then these store instructions have only one source register file. So the if so which means that if this source register file is ready in the processor, then so this one of the store instructions can be executed early. So which means that we can calculate the address of this store instruction as early as possible. Because why is it important? Because the store instruction is the write operation for memory. And then if the address is unknown, then the following load instruction cannot access the memory because of low hazard. Okay. And then so the store instruction access the cache, so which means that the store instruction update the memory. So which means that this is the committed on the this store instruction is committed on the memory. Of the following add instruction, so these instructions are dispatched to the integer issue queue. So 6, 7, 8. So we can easily calculate the execution cycles for this add instruction. How about the branch? If you see this branch instruction, so branch instruction just check the R3, and then you know this R3 is picked by sub instruction I8. So what's the problem? If you see this branch instruction, then branch instruction need to wait until the R3 is completed. So when the sub this I8 is completed, clock cycle number 11. So which means that this branch instruction can be issued at clock cycle number 12 after the R3 is completed. So branch is reserved at clock cycle number 14. Okay. So what's the problem? After this branch instruction, this is the branch instruction, and then we don't know the result of this branch instruction with the Tomasulo algorithm, because this branch instruction is not written back until the clock cycle number 14. How about this load instruction? This load instruction is after so if you see that this program code, then if the branch is taken, then it is going back to the first load instruction. And then this load instruction cannot be dispatched because this branch instruction. So if you see that this table, if the branch instruction is completed, so which means that the result of the branch instruction is reflected on the common data bus, okay, at clock cycle number 14. After that, this load instruction can be dispatched at clock cycle number 15. So what does that mean? So in this example, as you can see, because this is the out of order processor, so which means that inside of a basic block, these instructions can be dispatched every cycle. So which means that it's a CPI. So it looks like the CPI of this processor is 1. Okay, we just consume only 1 clock for every instruction. So the instruction can be dispatched every cycle. But when the branch instruction is encountered, until the branch instruction is completed, the following instructions cannot be dispatched. So this is the between I9 and I10 instructions, this processor will waste clock cycles, okay? Because this processor does not know the result of the branch instruction, so we cannot dispatch the next instructions, okay? The future instructions of the branch instruction. So these clock cycles are wasted, so performance is degraded. So if the branch is reserved, then the following instructions can be dispatched every cycle. Okay. So we can estimate how instructions are executed on the out of order processor using this table. Okay. So we can like some pipelining timing diagram. So actually the static pipeline is relatively simple. Then for the static pipeline architecture, then we can simply draw some it's very similar to this table, but so we can simply recognize how instructions are executed and how instructions are stored in the static pipeline architecture using the static pipeline timing diagram. For the out of the process architecture, we can use the table like this. Okay, so by estimating the clock cycle number for each instruction and then for each stage of this out of the processor architecture, then we can estimate how instructions are executed in a processor. Okay, so actually this table is so it's very good for making a problem using this table, out of the process architecture. Okay, so please try to understand this execution table of the out of the process architecture. Okay. Okay. Then, let's move on to the speculative execution. So actually the next slide is the dynamic branch prediction, but people explaining about this dynamic branch instruction, then let's see the speculative execution. So we learned that this advantage of the Thomas Law algorithm is branch instruction. So this is the barrier of instructions in a processor. What's the problem? Because of the branch instruction, we cannot exploit the instruction level parallelism efficiently because we cannot find available instructions after this branch instruction. So branch instruction is a barrier. Then how can you overcome this barrier of instructions? So we already know that after the branch instruction, there are many instructions actually. Okay, after branch instruction, we can find many instructions, but these instructions cannot be executed because when the branch instruction is encountered, the instruction path is diverged to the true path and then false path. But there are many branch instructions actually. So if you see some execution path of our program, then the execution path is diverged like this whenever the branch instruction is encountered in our program. So actually branch instruction is very critical. Then how can we improve the performance of out of order process architecture? So which means that how can we increase the number of available instructions? That is the idea of speculative execution. Okay. So let's think about the static pipeline architecture. Actually, we already learned about the branch predictor in the undergraduate course. Actually, we learned about the dynamic branch prediction actually. Then, so think about how the static pipeline architecture handle branch instruction or with the branch predictor. First, if the branch predictor predict the result of a branch instruction, right? Like true or false. If the prediction is hit, so which means that prediction is correct. So then it's very good. It's okay. The instructions are executed normally. Okay. So instead of, we don't need to flush any instructions in the pipelines. But if the branch prediction is missed, Okay, then how can you resolve this case? We flush pipelines. Okay, that's how we handle branch instructions in a static pipeline architecture. And then actually the same mechanism can be applied to the out of order processor. But what's the problem? Problem of the Thomas-Ull algorithm is that, so Thomas-Ull algorithm actually implement the out of order processing, so which means that the actually implement the out of order completion. And then in the Thomas-Ull algorithm, completion is equal to commit. So which means that when the instruction is completed, then result of instructions are updated to register file or memory. Okay. But if we avoid this situation, and then if we divide the completion and commit of instruction, and then before these instructions are committed on the processor, then if we can cancel the completed instruction, then we can implement the flush of instructions. Okay, so which means that flush of completed instructions. Then how can we implement this? So I already explained that when an instruction is executed, the instruction update the two parts, actually two components, so two data. So data on register and then data on memory. Okay, so actually the registers are updated by many instructions like archive or load, and blah blah blah. Many instructions update the register file. So what does that mean? When the instruction is updated, so when the instruction is completed, and then these completed results are stored in the temporary some memory component. It's a temporary storage, like here. Then we can postpone the commit of these instructions, right? So the result of these register, these instructions are stored temporarily in some temporary storage. So it's a completion state, but it's not committed to the register file. So when these instructions are committed, the branch is reserved, so which means that the prediction is reserved, and if this path, the instruction execution path is right, then we can commit this data on the register file. Okay, so that is the possible solution. Then how about the memory? So for the register file, we can make the temporary storage, and then the completed data can be stored in this temporary storage. And then when the instruction is committed, then the result in the temporary storage is reflected to the register file. Okay. How about the memory? The memory is updated by only store instruction. Then how can you solve this case? So actually the dependencies between store instruction and load instructions are already managed by load store queue, LSQ. Okay. Also, the store instruction, so store instruction can be executed. So only when the result, the branch is reserved. So it is because actually the register file, the size of the register file is very small, but the memory size is very large, so we cannot. It's not easy to manage the temporal storage for the memory instruction. So it's the memory data, but the memory is only updated by store instruction, and then actually before the store instruction is access the cache, which means that the memory, then store instruction is located in the load store queue. And then the data dependency between load and store instructions are managed inside of the load store queue. And the store instruction is only completed when the branch instruction is reserved. Okay. By doing this, we can divide the completion of instruction and commit of instruction. But only for the store instruction, when the store instruction is completed, the memory is updated. So we need to avoid this case. So which means that store instruction is completed only if the branch instruction is reserved. Okay, that is the main approach of the speculative execution. Okay, so we need to classify the approachable register file. Also, we need to distinguish the approachable register file. Also, we need to I explain about the approachable memory. Okay, so this is the main idea of the speculative execution. So main idea is that we just distinguish the completion of an instruction and then commit of the instruction. And then before instruction is committed, these instructions can be rolled back. So that means that it's canceled, which means that these completed instructions can be flushed. Okay. So for the normal instruction, actually the store instruction is pending until the branch is reserved. But for the normal instruction, for the register that access the registers, then I already explained that we need the temporary storage. So this temporary storage is implemented out of the processor. Then we can implement speculative execution. Okay. So this is the this is the architecture of the Thomas law algorithm with speculative execution. So as you can see, new structures, new functional units are included in this speculative execution. So like real buffer here. Then real buffer is some temporary storage for normal instruction, like instructions that access the register file. Okay, I already explained here. So real buffer is the main component of the speculative execution, that a processor that supports speculative execution. And then this is branch prediction buffer called the BPB, and then branch target buffer is also the main part of the speculative execution. So with the branch prediction buffer, then we this processor predict the result of the branch instruction, like conditional branch instruction. And then, so with the branch target buffer, the target of the branch instruction is stored. So it's a load, and then we can fetch the more instructions. We can fetch more instructions in the instruction cache. Okay. So this branch prediction buffer and then branch target buffer is used for predicting branch instruction. And then register alias table. So register alias table just track the status of registers. Okay. So I will explain about the register alias table later. So these are main components of the speculative execution. And you have to support the speculative execution, the these new structures are included in the Thomas law algorithm. Okay. So then so let's see what is different from the Thomas law algorithm with the speculative execution. Actually, if you see the structure of this speculative execution, then you can find, oh, actually the processor structure is very similar to the Thomas law algorithm, right? So ROB and then BPB and BTB and then register alias table. So these are the new components for speculative execution, right? And then the main architecture of this processor is very similar to the Thomas law algorithm. Okay, then let's see why these components are required for speculative execution. The first, branch prediction buffer and the branch target buffer. So we will also learn about the branch prediction buffer later. But if you see the branch prediction buffer and the branch target buffer, then you can find that this branch prediction buffer and branch target buffer is connected to the instruction fetch engine. Okay, so with this branch prediction buffer, the result of the branch instruction is predicted, and then branch target buffer estimate the target of the branch instruction. So BPB decides the taken or not taken of the branch instruction. And then BTB, branch target buffer. If the branch is taken, then we need to jump to the target of the branch instruction. So which means that if the branch is predicted as taken, then using the target branch target buffer, the target of the branch instruction is estimated. And then using this target, then instructions are fetched. And then fetched instructions are included in the instruction fetch queue, right? So why do we need branch prediction buffer and then branch target buffer? In order to fetch more instructions, okay? So more instructions are fetched, and then more instructions are included in the instruction fetch queue, right? So, and then dispatch is the same. So if so the instructions in instruction fetch queue is decoded and then dispatched to the issue queue of this backend of the out-of-board processor. And then why do we need the register alias table? So in this speculative execution, then we distinguish commit of instruction and then complete of instruction. So you need to remember that with in order to support the speculative execution, we need to distinguish completion and commit of instruction. Okay, so completion means that it's similar to in the static pipeline architecture, when the execution is performed by ALU, then the processor has the data for this instruction, the result of this instruction. It's the same. When the instruction is executed by this execution engine, then the result of this instruction is generated, and then this result is stored at a certain in a certain storage space. But so this is the completion state. So which means that the result is generated. The result is stored in some storage in the processor, but this result is not updated to register. This is the completion state of instruction. Okay. Commit means that the data is updated to the registers. Okay. So which means that registers have commit data. The register has, which means that it's updated data. Okay. So actually, now to support the speculative execution, we distinguish the completion and then commit of the instruction. So which means that the registers, so the registers have a different state also. In the out-of-order process, so in the Thomas law algorithm, we just distinguish the state of the register as the pending. The pending means that the instruction is dispatched, and then but the instruction is not completed yet. So which means that the instruction is dispatched to the issue queue, and then the destination of this instruction. So which means that the result of this instruction is not computed yet. This is the pending status. Then completed. So which means that in the Thomas law algorithm, completed means the execution of this instruction is completed and then it's updated immediately. But in the speculative execution, we distinguish completed and then commit. So actually the register file has three different states. The first state is the pending, it's the same. The register is the actually instruction is dispatched. So which means that, I mean, if this instruction, so if you see that this instruction, the destination register of this instruction is the R1. So I explain about the state of this register. Okay. So if you see that this register, the first possible state is the pending. So it means that the instruction is dispatched, but it's not yet completed. Okay. So what does that mean? A processor does not have data for this register. It should be calculated. It should be processed. So we don't know. It's unknown. It's a pending state. But if the execution is completed, then we can use this data. Okay. Another state is the completed. So which means that the instruction is completed, but this instruction is not yet committed. No? So completed, but not yet committed. This is the completed state. And then the last state is the committed. So which means the data, the data is updated to the register file. So register file has requested data. So register file has these three states. Pending state. So which means that we don't know the result of this register, but the execution will be the instruction will be executed. So in the near future, we can know the result of this register. This is the pending case, pending state. Completed. Execution of this register is completed. So processor has known values. for this register. Okay, but this value is not yet updated to the registers. So which means this value is stored in temporary storage. This is the completed state. Committed, so register has value, a known value, because the result is updated to registers. Okay, this is the committed. So register file has these three states for each register. The register alias table manages the status of registers. Okay, and there are three states: pending, completed, and committed. And then ROB. So this is the main feature of the speculative execution. So ROB tracks the dispatched order. So ROB tracks the order of dispatched instruction. Okay. And then, so the instruction is completed, then the result of instruction is stored in the ROB. Okay. So these are main feature of the ROB. So keep tracks the order of dispatched instruction here. So ROB is just a FIFO, is a first in, first out structure. And then, so ROB also holds the speculative value. So speculative value means that it's completed, but not yet committed. That is the meaning of speculative values of registers. So ROB is the temporary storage for not committed register data. Okay. So because of this ROB, then we can distinguish the complete state and then committed state of the instruction. Okay. This is the ROB. So let's take a 10-minute break, and then after the break, then I will explain about the speculative execution. So this is very important. The speculative execution is the main feature of the modern process architecture. So, and then it means that ROB, so real buffer, is actually the main feature of the modern out-of-order process architecture. So I hope every student can understand the role of the ROB and then how the speculative executions are implemented on this out-of-order processor. Okay, so let's take a 10-minute break, and then I will be back at 11:55. Okay, let's take a break. Okay, it's better. It looks like I'm teaching. I can feel I can feel like I'm teaching. Okay. Actually, this part is the very important part. So, okay. I think it's working. So this part is the very important part. So actually, understanding the behavior of ROB is critical for understanding how the out-of-order processor works in the modern process architecture. Okay, so this speculative execution is related to the security issue of the modern process architecture actually. So you know the very popular Spectre or meltdown. So these speculative attacks actually it should be called some vulnerability of the modern processors, because so attack is actually very hard hard to implement. But so Spectre and the meltdown is the kind of processor vulnerability, and then actually the attackers can take some secret data using this vulnerability of the processor. So but actually the Spectre or meltdown exploit the speculative execution. So this is actually the backbone of the modern processor architecture. So which means there is a very important architectural technique that can improve the performance of a processor. But by exploiting this speculative execution, the security attacks can happen, which means the attackers can exploit the vulnerability of process architecture. Okay, so actually, you know, so this is now this is not an easy part. So which means that it's I believe this the understanding the out-of-order process architecture and then speculative execution is a little bit tricky. So actually, if you have a textbook like the parallel process architecture, parallel process organization, maybe, yeah, parallel computer organization. So the name of the textbook is the Parallel Computer Organization and Design. So if you have a textbook, then you can read this part. So actually reading a textbook is very important. So please read the textbook to understand how the out-of-order processor with speculation works. Okay. So I already explained that speculative execution can be implemented using new structures called reorder buffer and branch prediction buffer, PT, and branch target buffer, and register alias table. Okay, so actually, if you read this slide, so these two parts of slide, I already explained about these slides. So this means that we can combine the three main ideas to implement the speculative execution. So it's a hardware supported speculation. So actually Thomas algorithm is the main baseline of out-of-order processing. Also, we can apply the dynamic branch prediction. So which means that with the dynamic branch prediction, we can predict the result of a branch instruction with high probability. Also, with the BTB, the branch target buffer, then we can know the target of the branch instruction. But actually, the target of the branch instruction is where we can get the target of the branch instruction is very easily, because actually, if you see the branch instruction here, okay. So for the most of conditional branch instruction, the target is actually fixed. So which means that if a branch instruction is once executed, then we can easily get the target of the branch instruction. Okay. So with the branch predict BPB and the BTB, then we can find more instructions to be executed. Okay. And then speculative execution. So which means with the ROB, then we can implement the speculative execution. This is so by combining three main ideas, then we can implement the hardware supported speculation. Then key idea, I already explained about the key ideas of this speculative execution. So you can read these sentences. Okay. And then also precise exception. I explained that with the Thomas law algorithm, we cannot support precise exception because Thomas law algorithm just implement the out of order completion, and I already explained that with the out of order completion, we cannot support precise exception. But with the speculative execution, we distinguish completion and commit of instructions. So with the speculative execution, the completion is out of order. Okay, so it's obvious because it's the baseline architecture is the same. It's the same to the Thomas law algorithm. So we support the out of order completion, but commit is in order. Understand? Dispatch is in order. So with the speculative execution, the dispatch is in order, and then but completion is out of order. Out of order, commit is in order. What does that mean? With the commit, it's very similar to. It's not right back. So the commit means that the result of instructions are updated to registers or memory. So this commit is because this commit is in order, so we can also support the exception handling when an instruction is committed. Okay, so which means that instruction commit is in order, so which means we can support in order exception handling. Okay, how can we call it? It's a in. So you need to remember this. So because the commit of an instruction is in order, then we can support precise exceptions. Okay. So this is the main feature. By distinguishing completion and commit of an instruction, we can support the in order commit, which means we can support precise exceptions. So this is very good feature of the out of order processor with speculation. Okay, so we added the new functional units like the ROB, PPB, PTB, and RIT. Okay, here. So, and then we use the ROB entry number for the new register tag. What does it mean? So I already explained that with the Thomas law algorithm, we can solve wow hazard and war hazard. And in order to solve the wow hazard or war hazard, we need to rename registers because the registers have different values, but just destination registers is the same for the different instructions. But if you distinguish these destination registers with the register renaming, we can solve wow hazard or war hazard. And then in the speculative execution, we solve the wow hazard and war hazard with the ROB entry number. What does that mean? Like this, add R1. So when an instruction is dispatched, so instruction is decoded and dispatched to the issue queue, and then this instruction is also included in the ROB. So ROB, as I explained, ROB tracks the order of dispatched instruction. Okay, ROB tracks order of dispatched instruction. So which means that not to track the order of dispatched instruction. When the instruction is dispatched, this instruction is registered. So which means the in-queued, because ROB is FIFO. So ROB is a FIFO, first in, first out. So instruction is in-queued in ROB. So in queue. Okay, in-queued. So which means that this instruction is registered in ROB. And the instruction is in-queued in ROB, is R1, the destination register of this instruction. The state of this register is changed to pending. Right. So between dispatch and completion, the status of a register is pending. Okay. So, and then its register number is tagged with the ROB entry number. Okay. So in the Thomas law algorithm, when the instruction is dispatched and the in-queued in the issue queue, then the tag is included in the destination register. And then with this tag, then we can resolve the wow hazard and the war hazard. And then in the speculative execution, the instruction is dispatched, and then this instruction is registered in the ROB. The ROB entry number is tagged to this destination register. Okay, so which means that RAT tracks the status of registers, and then for the corresponding destination register R1, for this R1, RAT changed the status of R1 as the pending, and also the RAT stores the ROB entry number. It's like ROB number for this register. Okay. So with the ROB entry number, the speculative execution solves wow hazard and war hazard. Okay. And then the instruction is completed by execution engine. Then the result is stored to ROB. Okay, so which means that the R1 of this add instruction is stored to ROB. But this is the completion. So which means each completion. So just the status is changed. Status of register is changed, but ROB entry number is maintained because this result is not yet updated to registers. And then after the committed, so when the instruction is resolved, so like which means that the branch instruction is resolved, and then the instructions are committed every cycle. Okay, so I said that the ROB is a FIFO. Okay, so it means that actually ROB has the 2 pointer. So if you just implement the FIFO queue, then we need to have 2 pointer, like the head pointer and the tail pointer, right? So you need to know the structure of the FIFO. Okay, so actually this ROB is the FIFO. So first the ROB is pointed by dispatch pointer and commit pointer. Okay. So it- so, so it looks like this. The new entry is registered for this direction. Okay, so by this dispatch pointer, the instructions are registered in ROB, and then it is the pointer goes to this direction here, and then when the instruction is committed, the instruction is committed by this commit pointer. So which means that the instruction is reserved. So which means the branch instruction can be reserved, and then every cycle the instruction is committed like by this commit pointer. So the commit pointer is moves also to this direction. By this commit point, an instruction is committed to the registers or memory. Okay, so in the ROB, if the instruction is committed, then it's changed to the committed. The status is changed to the committed, and then this instruction is popped out from the ROB, right? Because it's committed. Understand? So the instruction is dispatched. The instruction is registered in ROB by dispatch pointer. Okay. So and the instruction is committed. The instruction is committed by commit pointer. Then instruction is dequeued in the ROB. So this instruction is popped out from the ROB. Okay. So when the instruction is committed by the RIT, register alias table, the status of this R1, so because it's add R1, is changed to the committed. And then because the instruction is popped out from the ROB with no ROB number here. And then we can access this register with the register number from register file. Okay. Okay. So RIT keeps track the tags and the location of the latest register value. Okay. And then I explain how the RIT manage the target registers. Okay. So, this should be clear. So for this example, the destination of the add instruction is R1. Also, destination of register, the sub instruction is also R1. So, and then when the instruction is dispatched, the ROB entry number is assigned to this instruction, like the destination register of this instruction. So, because the instruction is registered to the different ROB entries, so this R1 has the ROB entry number 1, and then this R1 has the ROB entry number 2, for example. So because the different ROB entry numbers are assigned to the destination register, then we can distinguish these registers. It's the same to the tags of Thomas algorithm. So it's also same to the register renaming technique to solve the wow and war hazard. Understand? So that's how the Thomas algorithm with the speculation works. Okay. And then let's see the detailed operation of the speculative Thomas law. So then is the speculative out of order processor architecture. Okay, the first stage is the instruction fetch. Right. So instruction fetch is just to fetch the instruction from instruction cache. So like here, and then as I said, this instruction fetch engine is instruction fetch engine has the BPB and BTB, so we can perform the branch prediction. Also, the branch target is stored in the branch target buffer. And then based on the result of the branch prediction and then target of the branch instruction, then instructions are fetched and then included in the instruction fetch queue. Okay, so this part explains this operation. Then how about the dispatch? So this actually in the instruction fetch stage, only difference with the Thomas algorithm is BPB and BTB. So which means with the help of BPB and BTB, then we can fetch more instructions over conditional branch instruction, right? Okay, the instructions are included in the instruction fetch queue, IFQ. It's the same to the Thomas algorithm, and then it's decoded and dispatched. So if you see that this part is a little bit longer than the Thomas algorithm, but it's fine. Actually, as I already explained. So when the instruction is located at the end of the instruction fetch queue, then this instruction is decoded and dispatched. Okay. So when the instruction is dispatched, then something like add R1, R2, R3. So this is the example instruction. So if you see this instruction, then this instruction requires the two source registers, RS1 and RS2, and then have the one destination register. So that means that the result will be written back to this destination register. So for this instruction, instance, this instruction check the RAT, register alias table, to check the status of source registers. Okay, so and then as I explained, the RAT has the three different conditions like pending and completion and committed for each registers. So for example, let's check the R2. If the R2 is the pending status, then actually if the status is pending or completion, then this RAT has the valid ROE entry number. Right. Understand? And then the status is committed, then this register has the register number, like R2, which means that ROB entry number is invalid. Understand? So if the state is pending, then ROB entry number is just given to this source register. Okay, so ROB entry number. And then if the status is completion, then we can read the data from the ROB because the result is stored in the ROB. Okay, so we can read the data from the ROB. Like, okay. And then RD is updated. You know, for this add instruction, RD is R1 because, and then this add instruction is dispatched. So R1 is changed to the pending. Okay. And then I already explained that when an instruction is dispatched and this instruction is included in the ROB by dispatch pointer. Okay, so new entry is assigned to this instruction. So R1 has this ROB number. So ROB entry number of this instruction is assigned to the R1 by RAT. Understand? So this is the dispatch status. So I think my table is so good. I don't know. I can understand this function. So the instruction is decoded and dispatched, and ROB is assigned. And if the instruction is load or store instructions, then load store queue entry is also assigned to this instruction. Okay. And then I already explained about the status of registers in the RAT, register alias table. And then we can also think about the structure hazard of this out of the processor. So which means that so when the instruction is dispatched, this instruction should be registered in ROB. Also, it should be registered in the SQ. Also, if the instruction is load or store instruction, then we need to also assign the load store queue. So queue is also hardware components, which means that queue has limited number of entries. And then if all entries are already occupied, then we cannot register this instruction to this issue queue or ROB or load store queue. So in this case, the instruction cannot be dispatched, so which is the structure hazard of the out of order processor. So if these queues are full, then we cannot dispatch this instruction. Okay, this is the dispatch stage of speculative execution. So Thomas law with speculation. So the instruction is issued to the issue queue, and then also the instruction is registered to the ROB. Then, if the all operands are ready, like I2 and I3, also, and then if the hardware components are ready for execution, like we need to check the availability of the CDB. Also, we need to check the availability of execution engines. So if the hardware components are available, then we can issue instruction. Okay, it's same to the Thomas law algorithm. So the instruction is issued, and then the execution is completed, then the result is delivered to the common data bus. So you can find the common data bus. But let's see how common data bus is connected. So what is different? What is different from Thomas law algorithm, original Thomas law algorithm? So if you see the common data bus, you can see our common data bus is also connected to the issue queues. It's the same to the Thomas law algorithm. But in the Thomas law algorithm, common data bus is connected to the registers. But in the Thomas law with speculation, common data bus is connected to the ROB. Okay, so which means when the instruction execution is completed, the result is delivered to the first issue queues, because the issue queues has the pending registers, and the result is delivered to the ROB. Okay, delivered to the ROB. So which means that the completed result is stored in the ROB, and then the status is changed to the completion, the RAT. So, and then if the instruction in the issue queue has the pending registers, then also with the ROV number. So which means that when this is the destination of this instruction add, and then the ROB is assigned to this destination register. So which means when the execution is completed, the result is given to the common data bus. Also, the ROB entry number is given to the common data bus. Okay, so which means if this register is the pending status, then it is given to this issue queue. So which means the operands are stored in the issue queue of this issue queue of a certain entry, and the result is given to the ROB, and then the result is stored in the ROB. Okay, so issue is the same, and then completion, execution, and then RIT. So this slide explains this case, and then commit. So when the instruction is completed, then the status of this instruction is changed to the completion. And then by the commit pointer, the instruction is committed every cycle. Okay, it's committed and then committed and committed. When the instruction is committed, then the instruction is popped out from the ROB. Okay, and the instruction is committed, then the result of this instruction is stored in the ROB entry, like at R1. So then if the instruction is committed, this R1 is updated to the register file. So finally, the register file is updated. So the state of processor is updated. Okay, that is the speculative execution. So, and then how can we handle the branch misprediction? So which means that the branch is predicted, but the prediction is missed. Okay, so in this case, then in this speculative execution, the data is still exists in ROB by, so this is the commit point, and this is the dispatch point. So if you see the this ROB pointer, then these instructions are not committed yet. So the branch is reserved, and then but this prediction is mispredicted, and the prediction is missed, then we can move the commit pointer. No. At commit pointer. So commit pointer is the tail. So we can move the dispatch pointer. sorry. We can move the dispatch pointer. Okay. So which means that based on the result of a branch prediction, some instructions are dispatched, right? And then these instructions are executed, but this instruction is not yet completed, not yet committed. Okay. So when the branch misprediction is detected, then we just roll back ROB. Okay. So which means this dispatch pointer is moved to the location of the branch instruction, and so which means that actually the commit pointer, the commit pointer plus 1 actually, then we can roll back the dispatch of these instructions. Okay, so if you see this explanation on this slide, branch remains silent until the top of ROB. So which means that it's the commit pointer of the ROB. Okay, and when the branch is committed, so which means that we can know the result of a branch instruction. Then we can know the misprediction of the branch in this case, because it's the commit then if the branch is mispredicted, these instructions between commit and dispatch pointer is falsely dispatched and falsely being executed by processor. So we need to roll back these operations. So dispatch pointer is moved back to the commit pointer +1, and then new instructions are dispatched by the correct result of a branch instruction. So actually, the new instruction should be fetched because the result of a branch prediction is wrong. Okay. So the flush of ROB means that the ROB entries are initialized, and then the dispatch pointer is moved to the top of the ROB. So it's actually the commit pointer. So these instructions are canceled in the process. Understand? And then exceptions. So in order to support the precise exceptions, then exceptions are handled when the instruction is committed. Okay. So exceptions are flagged in ROB. So which means that we need to know the causes of exceptions. So why exception happens. So these are flagged in ROB and then remain silent. So which means that the exception is not handled. This exception is not handled until the instruction is ready to be committed. Okay. So when an instruction is committed, then exceptions are handled by this flag. So which means the causes of exceptions. And then we already learned how the exceptions are handled in the pipeline processor, like the static pipeline processor. When exception is detected, then the former instructions complete right back, right? And then the following instructions, the next instructions of this exception, the instruction that cause exceptions. So next instructions are flushed in the pipelines. And it's the same to this Thomas law with speculative execution. When the exceptions are handled and the instruction is committed, then the following instructions, the entire pipelines are flushed in this processor. So which means that, oh, this is the ROB, and then, oh, this instruction is at the head of the top of the ROB, like the commit pointer. And then exception is detected. So actually the exception is detected earlier than this commit, but exceptions are now committed, which means the exceptions are handled. So when the exception is committed, then all pipelines are flushed in the processor. Okay, so which means that the following instructions are flushed in the ROB. Also, the all following instructions are flushed in the backend. Okay, so which is some execution path in the processor. And the exception handlers are called, and then exception is handled, and then the program is resumed after this exception point. Okay, so the main point is that with the ROB, we can support precise exception. Okay, so exception. Okay, so memory hazard. So it's the same to the Thomas algorithm actually. So which means that in the memory, in order to handle the memory hazard, we have the load and store queue. So it's the same to the Thomas algorithm. And then store queue is split into the two parts, address part and then store data part. Okay, then you can apply some same approach for the this memory hazard. Okay. Okay. So, but actually the Thomas Law algorithm. So, so one of the feature of the speculative execution is that store instruction. So store instruction is executed when the instruction is in the top of ROB. So which means that when the instruction is committed, then store instruction is executed because the store instruction changes the data in memory. So this is some special part for the store instruction. And then let's see the memory disambiguation. So what does that mean? So memory disambiguation means that, so it's like this. So this is the store instruction and this is the load instruction. That's actually the load instruction try to access the data with the address A. But for this store instruction, we don't know the address of the store instruction. So I already explained about this situation in the Thomas Law algorithm. So in this case, so because we don't know the address of a store instruction, and then if the load instruction is executed, then we can expect the two possible cases, which means that it is A or A. And then because we already know the address of this load instruction, then load instruction can be executed, but problem is that we don't know the address of the store instruction. So if the load instruction is executed before this store instruction, so which means that before we know the address of this store instruction, and then if this address is different from the address of the load instruction, because then we don't need, this is very happy. Okay, the load instruction fetch the correct data from the memory, right? But if the unknown address of the store instruction is the same to the A, so which means that the address of the load instruction, this is unhappy. Okay, so because the load instruction fetch the wrong data from the memory. Okay, so which means that before knowing the address of the store instruction, then the load instruction cannot be executed. That's the problem. I already explained about the conservative approach. The conservative approach means that, actually, with a very low probability, but this can be possible. The unknown address of the store instruction can be the same to the address of load instruction. So, which means, in this case, if the load instruction is executed before the store instruction, then load instruction will have the wrong data, incorrect data. So we need to avoid this situation. So which means load instruction cannot be executed. This is the conservative approach. But usually this unknown address, usually, I said usually, is different from the address of the load instruction because the memory is very large. Okay. So it's very bad. It's not good for the performance of a processor. Because of this situation, very low probable situation, then we need to sacrifice the performance of a processor. We don't like. So conservative approach is the most safest approach, the most safe approach, but it's not good for the performance. Then how can we solve this situation? So it is called the dynamic memory disambiguation. So which means that we can execute load instruction. So we can execute load speculatively. So what does that mean? For this case, we don't know the address of the store instruction, but we know the address of load instruction. So we assume that the address of store instruction is different from the address of load instruction. It's just a prediction, like the branch prediction, right? It's just a prediction. We don't know because it's unknown. But why do you use the branch prediction? We use branch prediction because prediction rate is, so prediction hit rate is very high, right? If the branch predictions, the hit rate of the branch prediction is very low, we need to avoid branch prediction actually, because it's very bad for the performance of the processor. Okay, but because the hit rate of the branch prediction is very high, we use branch prediction. And this approach can be applied to the memory disambiguation. So with the high probability, the address of the store instruction is different from the address of load instruction, following load instruction. So we assume that, we don't know, but unknown address is different from the A. So load instruction is executed speculatively. Okay, load instruction is executed speculatively, and this speculation is hit. We don't need to roll back our execution. So which means that we don't need to roll back ROB with a very low probability. So this prediction can be missed. In this case, we can roll back ROB with the execution of the load instruction. And then we can start from this load instruction actually. Right. So main idea is that the same approach of the branch prediction can be applied to the dynamic memory disambiguation. Okay. So even though we don't know the address of the store instruction, load instruction can be executed speculatively. And then if this speculation fails, then we can roll back the ROB. But with the very high probability, speculation is hit. So we can improve the performance because the memory latency actually. Memory latency is critical for the performance of the processor, but so which means that if we can execute the load instruction as early as possible, it's good for the performance. Okay, but because of this store instruction, the load instruction cannot be executed. But we have already ROB, so which means we can roll back the execution of this load instruction. So like the branch instruction, then we can speculatively execute load instruction. This is the good advantage of the speculative processor. So let's see the clock cycles of this speculative Thomas algorithm, like this table. So if you see this table, that we can find that retire column is added. So retire is actually commit. So this terminology is a little bit different by textbook. So some textbook use the retire of the instruction because the instruction is retired from the ROB. So retired. So instruction is popped out from the ROB. And then I frequently use the commit, and then some textbook use the graduate. Okay. It's like a graduate of the PhD course. PhD. Okay, so we sometimes use the retire or commit or graduate for this column. Okay, graduate of the instruction or retirement of the instruction or commit of the instruction. But as you can see, this column is added a commit column or retire column. So actually the code is the same. The instructions are the same. But we require one more clock for the commit stage here. So dispatch issue here, and then this. So this add instruction requires F1 from the load instruction. So which means that this load instruction wait until the this data is completed in the processor. Okay, so when the CDB is completed at clock cycle number 6, and then the load instruction is issued at clock cycle number 7. Okay. Store instruction is split into the two parts, and then the store this data part requires the F2 from the add I3, so wait for F2. So the F2 is the delivered to the CDB, then it can be issued. So, the commit is in order. So, the dispatch is in order. So the commit is in order. But if you see the this CDB part, so actually it's a bit similar to the completion. So you can see that the CDB is the out of order. Understand? So if it says ready, then it can be committed. And branch instruction 9, and then branch instruction is to be issued when the R3 is ready. The feature of the speculative execution is LS, the next instruction of the branch instruction. So in the Thomas algorithm, this LS cannot be dispatched because of the branch instruction. But in the Thomas law with speculation, load instruction can be dispatched. Okay, so load instruction can be executed, and then here, and then also this instruction can be dispatched. So you need to be cautious of some conflict in the CDB. So for the I9, so when the I9 is issued, and just after the R3 is delivered via common data bus, then the common data bus will be completed with this LS. Also, the next cycle, the common data bus will be completed with the I11. So you need to also check the confliction of the common data bus. But this is the hardware resource. So if the common data bus is occupied, then we cannot use this instruction cannot use the common data bus. So we need to avoid this situation also. So this is the clock cycle of the speculative Thomas algorithm. The main feature is that after the branch instruction, the instruction can be executed. Okay, this is the Thomas law with speculation. Main part is retire. Yes, commit column. Okay, so I think okay, so I think I need to stop here, and then so actually my plan was to cover until register renaming, but I think I need to stop here. So, do you have any questions with the speculative execution? Okay, so and then as I mentioned before, so this part is a little bit tricky. So try to understand how the ROB or some other part works with the speculative Thomas law algorithm. Okay, so this is actually the main part of the modern process architecture, so like the Intel or AMD, also the ARM processors, you know, like the some application processors. So if you don't have any questions, and I will stop here. Then, thank you for your attention. Then see you in the next class. So I will also provide the online class only for the next class. Thank you guys. See you in the next class.